This is lecture number 9 of Econometrics Theory and Application. The sample regression function. Let's say it's not possible every time that we consider each and every observation or value of population and draw a regression line from that data. So we take samples, and with the help of these samples, we can define the behavior of overall population. The more samples we have, the more we can have the regression lines. Now we have to see that to how much extent the sample regression line is representing population regression line. Because it's difficult to observe the population data and to run a regression on it, we can take sample data from population data and draw a regression line and assume that this regression line is representing the population. For example, pretend that the population of this table was not known to us, and the only information we had was a randomly selected sample of y values for the fixed x values as given here in table A and table B. Unlike the previous table, this one, we have only one y value corresponding to the given x values. That is, each y given xi in table A is chosen randomly from similar y values corresponding to the same xi from the population of this table. Similarly, we have one more sample from population shown in table B. This is sample 1 and this is sample 2. We take data of 10 families in each of the samples. X is the income and Y is the consumption expenditures of families. For each level of income, we take consumption expenditure of one family. For example, for $80 income, consumption expenditure of 5 families are given in this table. If you can see here, for $80 income, we have 5 families whose consumption expenditure is mentioned over here. But we take consumption expenditure of one family. Like this, we have taken consumption of $70 against income of $80. That means we have selected the 4th family from this consumption expenditure data that is under the $80 income. This one. Likewise, for each level of income, we take consumption expenditure of one family. So we have taken samples, that is table A and table B, from the population data that is given over here for 60 families, and we have taken the data for 10 families, each value of y corresponding to x value. Now, regression lines based on 2 different samples. Now we draw 2 sample regression lines based on our samples given in table A and table B. Here, initially there were 60 families. We make 2 samples of 10 families each here. Then we draw two regression lines from these 2 samples. The more you have samples, the more regression lines you can draw here. Before that, We took data of 60 families and draw a population regression line by joining the mean values of consumption expenditure given income level that we did in our previous lecture. Now we are discussing sample here. We have the data of 10 families and draw the sample regression lines for these samples. So let's say here that SRF1 is the sample uh, regression line taken from table A or the first sample, and SRF2, that is sample regression function 2, is showing us a sample regression line that is drawn with the help of data taken in table B. Just by joining these dots, we are able to get the sample regression line for second sample, and by joining these cross marks we get the regression line for first sample first sample that is taken from table A. Now comes sample regression function. Here is the sample regression function with its own parameters, this one. That is yi hat is equals to beta 1 hat plus beta 2 hat xi. Where y hat is read as y hat or y cap, and it is the estimator of expected value of y given xi. Here beta 1 hat is the estimator of beta 1 from population. Beta 2 hat is the estimator of beta 2. Now the overall population, if you are looking here, this one, the overall population is a sort of an ideal that we don't have access to, and it's fairly stable. It has parameters, but we don't get at it directly. We take samples, and those samples have estimators. Those samples are statistics that are estimators of population parameters. So for samples we call them statistics. And for population we call them parameters. Here is one sample, this one, and here is the other sample. So finally we can understand different notations that are introduced here, that all are about regression functions. In this case these are two regression functions having these are, like you can say, simple regression function having two variables. We have discussed it in detail that a simple regression function means a function having two variables, one dependent and the other one independent variable. So a function having two variables, one dependent variable and one independent variable, is known as simple regression function. In regard to this larger population, we have a stochastic population regression function. It has a parameter and it has a stochastic or error term, because even if we have got a good equation here, reality is not going to necessarily conform to our straight line. So we have a stochastic or random error term here, this mu I. Now that's the part we are trying to figure out. We don't get direct access to it. Instead we take samples. For each sample we produce a sample regression function, and now we have statistics, and these are estimators. In this case the intercept, this one, it is an estimator of the population parameter, and here is the slope, this one, and it is the regression coefficient, and it is the estimator of population slope parameter, that is beta 2. So this is how we have got beta hat for the estimator. These beta hats are for estimators, and these betas are for the population parameters. If you recall that the observation don't fall directly on the line, so it's important to add this mu I hat, this one, if you observe here, which we now called residual. Mu I hat is known as residual. So stochastic or random error term corresponds to the residual, and it is a residual because if you think about those graphs which can actually observe the difference between an actual y and y that is predicted by the line, so this is a residual, but still in this case we now have what we really work with, which is the stochastic sample regression function. So this is known as stochastic regression function, this one, stochastic sample regression function. This is a stochastic sample regression function where we predict y, and then we observe that y is actually a function of estimators, intercept and a slope plus some residuals that we do expect, and so that that is the key difference between sample regression function, which we use to make inferences to draw inferences about the population regression function, this one. Actually we take this stochastic sample regression function to make inferences and to draw inferences about the population regression function, this one. Now comes sample and population regression lines. Our primary objective in regression analysis is to estimate the population regression function on the basis of sample regression function. This equation is for population. We cannot analyze this equation of population due to some constraints, so we estimate the sample regression function, that is yi is equals to beta 1 hat plus beta 2 hat xi plus residual. And this line, if you're looking here, this line is population regression line, and this one is the sample regression line. We selected a sample from population and draw a sample regression line here, this dotted line. There is a difference between these two lines. Here, this one, sample regression function is not a mirror of population regression function, as there is a difference between these two lines. If you can look at this diagram at this point, that is expected value of y given xi, this is the expected value of y given that the value of x of population regression function, and on x-axis there is weekly income, and on y-axis there is weekly consumption expenditure. So this point shows the average value of dependent variable, that is expected value of y given xi. Suppose that here y is the particular family whose expenditure, you can say that whose expenditure at this income level is at this point. and here mu I, this one is the error term, which is y minus expected value of y, which we get through the regression line, and this difference, as this mu I is the difference between yi minus expected value of y given x, and this difference from this point to this point, this difference is denoted by mu I, this one, and the sample point is here, that is yi hat, this one, that is the estimated value of y. As we have plotted this line with the help of sample data, the difference between yi and yi hat is denoted by mu I hat, this one, that is known as residual. Population random error is equals to this one, population random error, that is mu I, is equals to mu I hat, that is residual, plus difference between yi hat and the expected value of given value of y given x, this much. I'm repeating this line again, that you can see that the population random error, this mu I, is equals to mu I hat, that is residual, plus difference between yi hat and expected value of y given x, this one. So if mu I hat plus the difference between yi hat minus expected value of y given xi is equals to population error term, that is mu I. Now it's clear from here as well that for x is equals to xi, we have sample observation y is equals to yi. In terms of sample regression function, the observed yi can be expressed as yi is equals to yi hat plus mu I hat, that is residual. Now from here you can see that yi is equals to yi hat plus mu I hat, this one, and the difference between these 2 points, this point and this point, is equal to the residual, that is mu I hat. So mu I hat is equals to yi and yi hat. You can see that the difference between these 2 points, this one yi and yi hat, the difference between these 2 points is known as residual or mu I hat. In terms of population regression function, it can be observed as yi is equals to expected value of y given xi plus mu I. If we take the population regression function here, so we can say that yi is equals to expected value of y given xi plus mu I, this one, that is from this point to this point. This is the value for y1, that is expected value of y plus mu I. But for the sample, yi is equals to yi hat plus mu I hat. So this is for sample. You can say that yi is equals to yi hat plus mu I hat, that is the residual, and for population regression function, yi is equals to expected value of y given xi plus mu I. Now observe that beyond this point, that is point A, this is the point A, and beyond this point on the right hand side of point A, estimated value of yi hat overestimates the true population regression function. That means that sample regression line is above the population regression line, means that yi hat, that is from sample regression function, it overestimates the true population regression function. That population regression function line is below sample regression line. So we can say that yi hat overestimates the true population regression function. And if we see below this point A, that is on the left hand side of point A, sample regression function underestimates the true population regression function. Here sample regression function is below population regression function, so we can say that sample regression function underestimates the true population regression function. Now obviously from this figure, yi hat overestimates the true expected value of y given xi for the xi shown therein. By the same token, for any xi to the left of the point A on this side, this area, the sample regression function will underestimate the true population regression function. But you can readily see that such over and underestimation is inevitable because of sampling fluctuations. Here it is sample regression function underestimates the population regression function, and here sample regression function overestimates the population regression function. And this type of over and underestimation is inevitable just because of sampling fluctuations. Means that overestimation and underestimation varies with the fluctuation in sample. That is just because of the fluctuations in the sample data.